Hi everyone! In this video, we're going to look at different reactions that occur with conjugated pi systems. So in particular, we're going to look at electrophilic addition. All right, so let's say we have a conjugated pi system and we'll use 1,3-butadiene, which we talked about before. So again, those double bonds are conjugated because they're separated by one single bond. Now let's say we're going to add HBr across one of those double bonds. So let's assume we only have one equivalent of HBr, so just one molecule. All right, what would happen first? So remember, in addition reactions, the double bonds in our molecule are very electron rich, so they can donate electrons to something, and in this case, it's going to grab onto the hydrogen on our acid, and we'll leave behind electrons on bromine. Okay, so then we end up with, let's see, actually before I draw the product, what side will hydrogen add to? The more substituted side or the less substituted side? So this is a Markovnikov addition reaction, right? So the hydrogen will add to the side with more hydrogens, or the less substituted side. All right, so we'll draw the hydrogen adding to that side of the double bond, and we're left with a positive charge on, let's see, the other carbon, the more substituted carbon. Now we also have a bromide ion that's kind of hanging out there. And let's see, is there anything else we need to consider? So, for example, is there a more stable carbocation or maybe a different carbocation? Is there a more stable double bond that could form? Now, remember, this is an allylic carbocation, right? So there is a resonance structure. So those pi electrons can move over, and the charge on the carbon will be shared with another carbon. And that's actually going to stabilize our molecule. All right. Okay, so always remember to look for resonance structures. Now, let's look at our first resonance structure. That bromide ion is right there and it's ready to react. So it can react with that carbocation. And remember that if you have a carbocation, the nucleophile could attack from the front or from the back. So we'll end up with enantiomers as our products. But I'll just draw one of the enantiomers. And I'll just write plus En off to the side. Okay, but what about our other resonance structure? What if that is allowed to react with the bromide ion? So that will attack the carbocation and we'll end up with yet another product. And let me just count my carbons. So I have 1, 2, 3, 4 carbons. That works great. All right, now let's look at our products here. Let's look at the one on the left, and let's focus on that double bond. Now, is that double bond mono-substituted, di-substituted, tri, or tetra-substituted? It's mono-substituted. So there's only one substituent on that double bond. Okay, and then let's look at the double bond in our other product. Is that mono, di, tri, or tetra substituted? Di substituted, okay. So, which one is more stable? The yellow double bond or the blue double bond? The blue double bond. Okay, so that's the more stable alkene. And then the yellow double bond is the less stable alkene. All right, so let's talk also a little bit about the kinetics and the thermodynamics of these products. So the first product that we formed was able to form right away because that bromide ion was right there. It was ready to attack the carbocation. And so that would be our kinetic product because it is produced more quickly. All right, so let's look at our other product. Now, the other product came from our intermediate, which was the second resonance structure. And that's actually going to be our thermodynamic product because the product is more stable. We have a di-substituted alkene as a result of that reaction with the second resonance structure. So that's the thermodynamic product. And we'll go over kinetic versus thermodynamic again on the next slide. I know it's probably been a while since you've even thought about kinetic versus thermodynamic, so we'll go over that again. Okay, so again, the first product is the kinetic product because the bromide ion is closer to the carbocation. All right. Now, the other thing to note is where the hydrogen and the bromine added on each of our products. So if we look at our kinetic product, let's start on the right carbon and we'll just number across. Notice that the hydrogen and the bromine added to carbons 1 and 2. So we would also call this the 1,2 addition product. If we look at our other product, let's see, and we number the carbons, 1, 2, 3, and 4. Notice that the hydrogen and the bromine added to the first and the fourth carbon. So this will be called the 1,4 addition product. And I'm just going to abbreviate product as PDT. So the kinetic product, or the 1,2 addition product, is favored at lower temperatures. And the thermodynamic product is favored at higher temperatures. Okay, so let's just kind of review why the kinetic product is favored at lower temperatures and why the thermodynamic product is favored at higher temperatures. And we'll also go over kinetics versus thermodynamics a little bit as well, just to review. All right, so let's draw an energy or a reaction coordinate diagram. So we have energy on the y-axis, and then we have our reaction progress on the x-axis. So again, we're starting with 1,3-butadiene, and that has a certain amount of energy to start. Then, once we react that with our HBr, hydrogen is going to add to the least substituted carbon on one of the double bonds, and then we get our intermediates. And then we'll see a reaction pathway for the addition of bromine to the second carbon. And then we'll see a reaction pathway for the addition of the bromine to the fourth carbon. Now, the first step in that one is the same. So that's going to follow the same energy pathway. But in the second step, when we add the bromine, now that activation energy is going to be higher, but the product is going to have a lower energy, or it will be more stable. All right, so let's just write, we have a proton transfer in this first step, and that's the same for both products. So first we add the proton, and let's just go back. So again, we're adding that proton to the first carbon, regardless of whether we're going through the kinetic pathway or the thermodynamic pathway. But now, once we get to the intermediate, now we have two possible products. And again, remember the kinetic product is favored at lower temperatures. The thermodynamic product is favored at higher temperatures. All right, so the blue line has a lower activation energy. So the activation barrier is really, really low. And then the product is less stable because it has a higher energy. So this is the kinetic pathway. And the product is the 1,2 addition product. So again, this product forms really quickly, but it's not necessarily the most stable. Now, if we look at the red pathway, the activation energy is greater, and this is the thermodynamic pathway. But the product is more stable. Now, this could actually be either the 1,2 addition or the 1,4 addition product. It kind of depends. So I'm just going to say that in general, the thermodynamic product is the more stable product. And let's just draw little pictures of our products here. So again, the kinetic product was the 1,2 addition. And the thermodynamic product was the 1,4 addition product. Okay, so again, just to summarize, the thermodynamic product is favored at higher temperatures due to greater activation energy. And then the kinetic product is favored at lower temperatures. So you could control which product you end up with. You could either keep temperatures colder, or you could increase the temperature and try to get a specific product. Okay, so let's look at an example, and you can kind of try this one on your own and see if you can figure out which product is favored. All right, so let's say we have another conjugated pi system. Okay, and this time we have a ring structure. And let's say we're adding one equivalent of HBr again. And let's say we're at cold temperatures. All right, so see if you can draw the intermediates and the two products, the 1,2 addition product and the 1,4 addition product, and see if you can figure out which one would be the major product. So feel free to pause the video and try this on your own first, and when you unpause, we'll go over it together. Okay, so let's see if we can draw our intermediates. So we know that one of these double bonds will grab onto that hydrogen on HBr. And again, our starting material is symmetrical, so it doesn't really matter which double bond takes that hydrogen. And we'll leave electrons behind on bromine. And then, which carbon will hydrogen add to, the less substituted or the more substituted carbon? The less substituted carbon, which is the one at the top. All right, so that will give us a tertiary carbocation there, and then we still have our other double bond down below. All right, now let's draw the resonance structure. So that double bond can move up to share the charge on carbon with another carbon. All right, so that positive charge has moved down below, but we do have our two resonance structures. Now remember, the first resonance structure, bromide is close by and it's hanging around because it just lost that hydrogen, so it's kind of sitting nearby. So for the product there, bromine can come from above or from below. So we get enantiomers. I'll just draw one of them. And we'll write plus En for the other enantiomer. Okay, and then once our other resonance structure has formed, the bromide ion will attack the positively charged carbon, and we should end up with our other product. Okay, now would that one form an enantiomer? So if we look at the carbon that bromine is bonded to, is that a stereocenter? Yes, it is a stereocenter, so that would form enantiomers. So I'll just draw one of them. I'll put bromine in a wedge, and I'll just write plus En off to the side. And I'll put a little asterisk next to the different stereocenters there. All right, so let's look at our first product on the left. And let's look at the double bond. Is that mono substituted, di substituted, tri or tetra substituted? Tri substituted. It has 3 different groups attached. And I'm just going to abbreviate tri substituted there. Okay, what about the other product on the right? Is the double bond mono, di, tri, or tetra substituted? It's tetra substituted. Okay, so which one is more stable? The yellow double bond or the blue double bond? The blue double bond, because it's more substituted. So we'll write that that is the more stable alkene. The other double bond is the less stable alkene. Okay, so looking at these two products, which one would you expect to be the thermodynamic product or the more stable product? The one on the right, the tetra-substituted double bond. Okay, and let's see, the other product is the one that would form faster since bromide is right nearby. So that would be the kinetic product. Okay, now let's figure out which one of these is the 1,2 addition product. The left one or the right one? The left product, because hydrogen and bromine added to the first and second carbons. So for instance, if we look at our starting material, we could number around the ring there. And we're not numbering this according to necessarily how we would name it, but we're just kind of showing where those double bonds are. All right, so we would add hydrogen and bromine to the first and second carbons there. So that is the 1,2 addition product. Okay, and then what about our other product? Well, that must be the 1,4 addition product. Okay, now let's try to figure out which one of these would be the major product. And remember, we performed this reaction at cold temperatures. So which product is favored at cold temperatures? The kinetic or the thermodynamic product? The kinetic product. So this would be the major product because we were at cold temperatures. So again, you can use temperature to control which product you end up with. So even though the kinetic product is the less stable product, if we lower the temperature, we can still form that product over the other one. Okay, and now let's look at one more example problem. This one will be a challenge problem. Okay, so I'm going to give you a conjugated pi system again. So what I'm going to do, this is a 7-membered ring. So I'm going to draw 7 dots in a circle. Let's see, 1, 2, 3, 4, 5, 6, 7. Oh, those aren't very equally spaced. Let's see if I can do this a little bit better. That's a little bit better. And then I'm going to connect all of the dots. It's a little messy, but that's okay. And then we're going to put our conjugated pi system in there, add a couple methyl groups. And now, let's say we're adding HBr, so 1 equivalent, and this time the temperature will be hot. So see if you can figure out what the intermediates are and what the products are. And then see if you can figure out which product would be the major product. Again, this one's a little challenging. So once you're done trying the problem on your own, you can unpause the video and we'll go over it together. Okay, so let's show one of our double bonds grabbing a hydrogen, and we'll leave electrons behind on bromine. All right, let's see if I can draw a better 7-membered ring this time. This is good practice. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, this one's a little better, maybe, a little more symmetrical. Let's see, so we're adding hydrogen to that double bond. Now, normally we said that hydrogen would add to the less substituted carbon, and then we would form the tertiary carbocation, right? So it might look like that. But remember, we have a double bond right next door there, and that can help us produce a resonance structure. Also, remember, resonance is more stable than a tertiary carbocation, a secondary, a primary, and a methyl. So that means in this case, hydrogen is actually going to add to the more substituted carbon, so that we can then form a resonance structure. So even though that carbocation is a secondary carbocation, it can go through resonance and that charge will be shared with another carbon, which is way more stable than just a tertiary carbocation. All right, so let's draw our resonance structure. Again, it doesn't have to be perfect. Obviously, mine are not perfect. They're a little messy here. Okay, and now our charge will be on a tertiary carbon. Okay, so again, let's just make a little note off to the side. H will add to more substituted carbon because that allows for resonance, which is more stable. Okay. All right, so now that we have our intermediates, we know that with the first intermediate, bromide is close by, so it can attack right away, and it can attack from behind or from above. Okay, so let's try to draw the product here. All right, so bromine, is going to add to that carbon. Now, you might be wondering, isn't that a stereocenter? So shouldn't we be drawing a wedge or a dash? Yes, it is a stereocenter, but notice that the carbon up above is also a stereocenter. So we have two stereocenters, and then we still have our double bond. So this could potentially end up being four different products. We could have RR, SS, RS, or SR. So there's a lot of possibilities here. And this is partly why this is a challenge problem, because there's so much going on. All right, so now let's look at our other products. So in this scenario, bromide will add to, again, that positive carbon. And it could add from above or it could add from behind. So let's see, 1, 2, 3, 4, 5, 6, 7. Okay. So what about this molecule? Are there more than one stereocenters? Yes. So we have a stereocenter where bromine added, and then the other carbon with a methyl group is also a stereocenter. So again, this could produce four possible products. Okay, so now let's talk about our alkenes, our double bonds. For the yellow one, is that mono, di, tri, or tetra substituted? Tri substituted. All right, and what about our other product? Is that double bond mono, di, tri, or tetra substituted? It is di substituted. It only has two groups bonded to it. All right, so which one is more stable, the left product or the right product? The left one has a more stable alkene. All right, now let's figure out which one is the kinetic product. The product on the left or the product on the right? So the product on the left is the kinetic product because the bromide was just right there, ready to attack. And this is also the 1,2 addition product. So that automatically means it's the kinetic product. Okay, and which product is the thermodynamic product? So remember, the thermodynamic product is the more stable product. So which one is more stable? The product on the left. Okay, so far we've seen that the thermodynamic product is usually the 1,4 addition product. And our product on the right is the 1,4 addition product. However, it's the less stable product because its alkene is only di substituted. So the product on the left is both the kinetic product and the thermodynamic product. All right, so this is a weird, example where you might have one product that is super stable. It is formed really quickly, so it's both kinetic and thermodynamic. Okay, so knowing all of that, which product do you think is the major product? The one on the left. And the one on the right is going to be very, very minor. It's not going to form to a significant extent, again, because the product on the right is more stable and it forms faster. Okay, so let's just summarize everything we've learned in this video. So we said that the kinetic product is the 1,2 addition product. And that's because the bromide ion will be closer to the carbocation. So the reaction happens quickly. And then we said that the thermodynamic product is the most stable product. So it's not necessarily the 1,4 addition product, but it is going to always be the more substituted alkene. And then we saw in the last example, the challenge problem, that sometimes the kinetic product is also the thermodynamic product. Okay, so we'll stop there today. In the next video, we're going to start discussing pericyclic reactions. So we'll talk about the Diels-Alder reaction, and then we'll also go back and apply some of those molecular orbitals. So remember to keep that in mind. Don't forget about molecular orbitals just yet, and I will see you then.